Landsat 9 is 15 feet tall, 10 feet deep, and 10 feet long. Once in orbit, it will deploy a 32-foot-long solar panel and 4-foot-long Earth shield. With fuel, it weighs almost 7,200 pounds. The satellite has two main instruments, Operational Land Imager 2 for reflective band data and Thermal Infrared Sensor 2 for thermal infrared bands. It will capture 700 photos each day and travel nearly 17,000 miles per hour.
25. Status check. Go Atlas.
Go Centaur.
Go Landsat 9.
And there it is, the word to launch Landsat 9.
T-minus 10.
9, 8, 7, 6, 5, 4, 3, 2, 1. Engine ignition. And liftoff. Liftoff of an Atlas V rocket and Landsat 9, continuing the legacy of an irreplaceable 50-year record on our ever-changing planet.
Control system response looks good. RD-180 engine operating parameters continue to look good. Vehicle has begun the pitch over maneuver. Body rates look good.
That pitch over maneuver heading it to the south towards Southern California and down to Mexico.
Now passing 40 seconds into flight. Engine operating parameters continue to look good. Pump speeds and injector pressures all within expected ranges.
There's a shot from our tracker cam above the marine layer.
Now 55 seconds into flight. Vehicle is now completing the pitch over maneuver. Body rate responses continue to look good. 3 minutes remaining in the boost phase of flight. Pump speeds and injector pressures on the RD-180 continue to look good. Body rates continuing to look good. And at 1 minute 20 seconds into flight, Atlas is now supersonic, vehicle passing Mach 1.
A critical moment for the rocket.
And vehicle is now passing max Q, maximum dynamic pressure. RD-180 performance continues to look good throughout boost phase. Engine's now throttling down slightly as expected. Engine response looks good.
That throttle down reduces the stress on the 19-story tall vehicle.
At 1 minute 50 seconds into flight, vehicle is now 10.7, 13 miles in altitude, 7.9 miles downrange distance, traveling at 1,500 miles per hour. Now just under 2 minutes remaining in the boost phase of flight. At 2 minutes 18 seconds, the Atlas V vehicle now weighs just 1/2 of its liftoff weight. And vehicle's gone to closed loop guidance. Body rates indicating a slight adjustment can be expected for this phase of flight.
There's a beautiful shot right there, looking back towards the planet. And see the plume from the RD-180.
And the reaction control system on the Centaur is now pressurizing to flight levels. System pressure response looks good.
So the reaction control system on Centaur, they're prepping it.
RD-180 engine operating parameters continue to look good throughout boost phase. Body rates remain stable.
Coming up in 60 seconds, the booster engines will cut off.
Flight. Approximately 1 minute remaining now until booster engine cutoff.
Our tracker shot getting a great...
And now 3 minutes 15 seconds into flight. Atlas is 48 miles in altitude, 70 miles downrange distance, traveling at 5,600 miles per hour.
Great shot as it goes out over the southern Pacific.
Pump speeds and injector pressures on RD-180 continue to look good throughout boost phase. And the Atlas V is now throttling to maintain a constant 5G acceleration limit. Engine response looks good.
Speed currently 7,700 miles per hour.
Centaur's begun boost phase chill down. Now throttling to maintain a constant 4.6G acceleration limit in preparation for BECO.
This is where the booster engine cuts off and then separates.
And we have BECO booster engine cutoff standing by for stage set. And we have good indication of Atlas Centaur separation. We have pre-start on the RL-10, standing by for ignition.
And there you see the separation.
We have ignition and full thrust on the RL-10. Chamber pressure looks good. Body rates look good.
Beautiful shot of the booster falling away as you're looking
and
down.
We have good indication of payload fairing jettison.
And you should see the
This
payload
first burn
fairing.
today
Sometimes they come around the
approximately
side.
12 minutes, 11 seconds.
There you see one.
RL-10 performance continues to look good in the early part of this first burn. Now passing 4 minutes, 47 seconds into flight.
So we're in a good point, Mick. Flight is looking good. We're going to monitor the situation here. But what a beautiful launch. What a beautiful flight so far.
5 minutes.
But there's still a lot of work to do.
Yeah, absolutely. A lot of work to go on, but beautiful shot there of the RL-10 engine in space, sending Landsat 9 onto its orbit. A great launch this morning. So excited for this.
We're getting some of that orbital sunrise on the engine bell there, and that's just a neat look as you look back
All right,
at
there
our
is a
planet.
live view on your screen now of Landsat on its way into orbit. Turning now to one of the many practical applications of Landsat, the U.S. Department of Agriculture uses it to track annual yield of every crop grown in the United States. Disaster managers can see impacts from floods and other natural disasters. Resource managers can use the data to direct crop rotation and monitor water use. Take a look.
America has always been a fertile land. Grasslands and forests and farms, from sea to shining sea. The U.S. Department of Agriculture tracks how many acres and the annual yield for every crop produced. From the big ones like corn, wheat, soy, to regional crops like cotton, rice, citrus. They track every year using data from Landsat satellites and others, combined with data from surveys on the ground. Landsat satellites see detail at the human scale, about the size of a baseball diamond, and can image individual farm fields. The program started in 1997 with North Dakota as an experiment. Other states became interested, and the program grew. In 2008, Landsat data became free to use, and the USDA could afford to map 48 states. During the growing season, the data helps estimate crop yields, which helps farmers and traders set prices for the harvest. Thanks to Landsat's detailed view, the USDA tabulates stats crop by crop, county by county, and state by state. At the end of each year, the data set is released to the public, and it is a beautiful sight. The patchwork of corn in yellow and soybeans in green in the Midwest. The diversity of crops in California's Central Valley. The clusters of citrus in Florida and California and Texas. We can see changes in farming through the years. The easiest to see is crop rotation in the Midwest, cycling between corn and soybeans. In northern North Dakota, there is a shift from barley and wheat to soybeans and canola. And we see an increase in cotton fields, shown in red, in Texas and Oklahoma. Thanks to the free and open access to Landsat data, the U.S. Department of Agriculture is providing our farmers with accurate data and helping maintain our nation's food supply.
Landsat 7 was launched in 1999 from Vandenberg Space Force Base. And since going into orbit, the satellite far exceeded its 5-year mission lifespan. But now it's running low on fuel. Instead of becoming yet another piece of space junk, Landsat 7 has a new mission. As the host satellite for an on-orbit refueling spacecraft called OSAM-1, which stands for On-Orbit Servicing Assembly and Manufacturing 1. Here's how it'll work. Landsat 7 will lower its orbit while waiting for OSAM-1 to launch. Once in space, OSAM-1 will autonomously rendezvous with Landsat 7. And when OSAM-1 gets close enough, The robotic arm will attach the gripper tool from off of its payload deck. With a shoulder, elbow, and a wrist, the robotic arm has a range of motion similar to a human arm, making it ideal for this complex and dexterous mission. OSAM-1 then catches Landsat 7 by the Marmon ring, which is how it attached to the rocket when it launched. Once ground operators nestle the satellite onto OSAM-1's 3 berthing posts, the autonomous pit stop in space begins. A cutting wheel removes the thermal blanket off the original fuel valve panel, which was never intended for a refueling. Ground operators will then use OSAM's advanced tool drive system to prepare the valves. The first will cut the lock wire that secures the valves. Then a removal tool will spin the cap off and stow it safely on the servicer. Now it's time to fill her up. The Hypergol refueling tool is connected by a hose to an onboard fuel tank. So when the nozzle is guided over the original fuel valve, more than 100 kilograms of hydrazine, similar to jet fuel, will be pumped into Landsat 7. The on-orbit refueling is expected to give Landsat 7 enough fuel to safely deorbit to make way for future science missions. And that extra fuel will allow Landsat 7 to continue on and re-enter Earth's atmosphere, which is important, keeping space junk clear out. That'll send it back down into Earth's atmosphere where it will burn up. And then that, Mick, makes way for another spacecraft to then take its place in that orbit.